Hello, this is Simon from Reigate Maths, and you're watching another video on the integration series in the A-Level Maths syllabus. This is the second year content, and this is the third video in our series on differential equations. This video is focusing on modelling with differential equations. The thing with modelling is there are two elements to it. One is forming a differential equation given some information. The second is then solving it. Sometimes you won't need to do the first part, but we're going to look at some key ideas anyway, so you can, when you look at a differential equation or a modelling question, you can think, okay, I know how to approach this question. Because it's all well and good just going through a ton of examples, but if you don't learn what statements to look at, it becomes very difficult to replicate. So we're not going to go through any examples of that, we're just going to discuss some key ideas. So, the first key idea is it's often talking about the rates. So a rate is often dy by dt, okay, or rate of change of y, or population might be p. We're going to use y for the sake of going through some bits here. But because we're talking about rates, we're always going to have t in the denominator, where t is time. So something that you might see a lot of is something is increasing or decreasing at a constant rate. So this means that our derivative is going to be equal to just a number. You may be told what that number is, you might not. But it's important you know that that's what a constant rate means. So, a number. This example here is increasing at a constant rate because our rate is positive. We might have minus k for decreasing. So the question may say, y represents the population of a town. Using data, we have found that the town's population is increasing at a constant rate. This would be your differential equation. dy by dt equals k. And it would be people per year, or something like that. Some unit of time, or some unit with respect to time. So that's kind of one idea, but that's the most simplistic version that you could get. Even simpler is if they give you what k is, which is nice. What they tend to do more is proportional to. So if you think about a population that grows, the more people there are, the quicker the population grows. So very typically, population is proportional to the number of people there are. So you may well remember from GCSE this symbol for proportional to. So for the purposes of this kind of example, we're going to say proportional to y. This is not an equation. So although it's useful to think about, this is not something you should be writing in the exam. We need to change this into an equation. And we do that by changing the sort of proportionality symbol into equals ky. So this may well be y is increasing at a rate proportional to y. This would be the differential equation. It might be proportional to y minus 7, or 7 minus y, or something like that. Or the difference in two things. So you'll have to adapt what we look at here to whatever the question is. But hopefully, kind of going through bits like this, it'll give you some idea and give you kind of a guidance. But as I said, this may not be something you have to do in the exam. You might just get given the differential equation. Typically, if you have to form it yourself and then solve it, the differential equation will be easier than if they just give it to you. If they just give it to you, they tend to be more difficult ones. The last one we're going to look at is inversely proportional. And again, we're going to look at inversely proportional to y, but it could change. We might have, we might have y squared, for instance. Might be the rate of change of population is decreasing or the population is decreasing at a rate that is inversely proportional to the square of the number of people. Something crazy like that. So it's still proportional. So they're going to be equals k, but the inverse means that if it's inversely proportional to y squared, the y squared is underneath the k. Likewise, if it's decreasing, it would be a minus. And so that idea here isn't just for constant rates. If it's increasing, it's positive. If it's decreasing, it's negative, which is really important. So these kind of are the major ideas for forming your own differential equation. The rest of it is sort of adapting these to a specific question. The only ones where it doesn't do this are kind of crazy trig ones, where it's looking at tides which change according to a particular wavelength, but those aren't so common, so we're not going to focus on those in the videos now. So this is the final example we're going to go through. It is a much more in-depth example, and we're going to add later parts of the question as we go through, but I'm just going to take it step by step. So water in a plant is held in a cylindrical tank of diameter 20 meters. Water flows out of the bottom of the tank at a rate proportional to the cube root of the volume. Show that t minutes after the tap is opened, dh by dt equals minus k cube root h for some constant k. Okay, didn't write down that it's coming out of a tap, but that's okay. So this is kind of the forming the differential equation side of things that we looked at. So let's have a look at the question itself, because this is the key thing. Is water flows out, which means that the water is flowing, so our rate of change of volume is going to be negative because the volume is going down. It's proportional to cube root of the volume. So this information all tells us that dv by dt is going to be equal to minus k times the cube root of v. Now, this is something really important. So what I've done here is something that students typically do. Is go, okay, dv by dt, because I've been given it, minus k cube root of v. Why shouldn't we use k? Well, because we've got k in the answer we're trying to get to. This is not this. So the variable that we use here should be different. So we're going to change it for a different letter. Let's just use C for the sake of argument. You can use any letter you like, just as long as you don't use K. Now, for some constant K means we're not going to work K out. K is going to probably be quite unpleasant. So we're just going to have something there instead. Now notice, we want dh by dt. We have dv by dt. So we need a way to get from here to here. And this is in the connected rates of change section of the syllabus, which is a previous video should you want to go and watch it. So we have dv by dt, we want dh by dt. So what we might want to do is write over here the way that they link together. So we want dh by dt, we have dv by dt, we need to times it by something to get here. We're going to times it by dh by dv. So we now need to link. So this is step one, is writing this. We now need to find this bit here. So we need an equation that links v to h. Conveniently, this is the height of the water. The water is in a cylindrical shape, and we can work out the volume of water. So the volume is going to be pi r squared, so base, so the area of the cross section, times h. We know the diameter is 20, so the radius is 10. So v is going to be 100 pi h, which means that dv by dh is going to be 100 pi. So therefore, dh by dt, the thing we're trying to find, is dv by dt times dh by dv, which is going to be 1 over this. So this is minus c, cube root of v, times 1 over 100 pi. We're now starting to get towards our answer, but if we look, our answer has h in it. Our current statement has v in it, so we also need to change that as well. So we end up with minus c cube root of 100 pi h, because we had v here, over 100 pi. The last thing we need to do is write it in this form. So we've got minus c times the cube root of 100 pi over 100 pi times the cube root of h. So remember when I said that k would probably come out as really unpleasant? We can see that. The thing with this question, and going on to later, we're never actually going to write this down. This is a thing that we're just going to ignore for now. We're never going to calculate c, because we're just going to write this as minus k root h, where k equals c times the cube root of 100 pi over 100 pi. Now we could write that a little bit tidier, but we don't need to, because we're never going to go over this. We're never going to use this statement again, because for the next part of the question, this is where we're going to start. And that's the thing with this question and questions of this type, is the first step is a show that, which means if you can't do this, you can still do later parts of the question. So here's our part B. Show that the general solution to this differential equation can be written as h equals p minus qt to the 3 over 2, where p and q are constants. So notice how we still don't have any numbers in there. But it says the general solution, which means we're going to be using this. So we've got the dh by dt is minus k h to the 3rd. I'm writing it like that immediately so that we can start to tidy things up. So this is now the differential equation we solve. We have h is on the left, because dh is on the top, and t is on the right, because dt is on the bottom. Tip with solving differential equations where we've got something like this, k times a variable. Leave numbers on the right. generally it's designed so that that is easier. Leave numbers on the right. So we're going to separate the variables, moving the h over to the left-hand side. Remember, we changed the power because we're doing 1 over h to the third, which is the same as h to the minus a third. Then we're going to integrate minus k with respect to t. Integrating as normal, we end up with increase the power by 1 and then divide by the new power. So on the left hand side, that integration is relatively straightforward. K is a number, so when we integrate a number, we just stick our variable next to it. So we've got minus kt plus a constant. Now, traditionally, you shouldn't use letters that you have already used. So we've already used C in part A, so we shouldn't use C again. So I'm just going to use a different letter. It doesn't matter what letter you use as long as you haven't used it again, or you haven't used it before, or you can see it's one we're going to use here. So it's fine. Let's have a look at what we're trying to get to. So notice how in the first part of the question, we didn't work out k. We got some messy thing that we just said, okay, we're not fussed about that, we're just going to call it k. We're going to do the same thing here. We're going to get something very messy, probably, here, but then we're just going to say, well, they're still numbers, so let's just give them names. So we're going to do that. So let's multiply through, because we're trying to get h on its own. Whoops. So h to the 2 over 3 is 2/3 m minus 2/3 kt. So if you look at what we're trying to get to, we can see that this is pretty much the bracket, just the constants have different names. So I'm just going to change them now. That's fine, we're allowed to do that. Because all we're doing is giving a number a new name, which, as hopefully you've seen with this example, is really useful. Because don't forget, k was equal to c times the cube root of 100 pi all over 100 pi. It's not nice. So we initially gave it a new name of k, we're now giving it a new name of q. Because it makes then this equation very easy to manipulate and use. Because it doesn't matter what k is. Remember, k is just a number. So if we can work out q, we don't need to work out k, because all it is just the coefficient of t in our final answer. So for our part C, we're now given boundary conditions. The important thing with this, compared to things we did in the previous video, is we are given 2 boundary conditions. Why? Because we have 2 constants. So if you have 2 constants, this is something that they will do. They will give you enough boundary conditions to work out both constants. So let's write them down in terms of the variables that we've got. Initially, so when t equals 0, the height is 27. And then when t is 10, remembering t is time in minutes, so be careful with that. That's something that they might try and trick you with, is to say, oh, t is in hours, 15 minutes later. So you might need to change your units. So do watch out for that. But in this case, t is minutes. Typically, they won't do that for this type of question, because they're aware that that would not, it's not that it would be unfair, is that it's so easy to miss when you're doing a big question like this. It's not potentially representative of you being able to do this question. It's kind of trying to trick you. So they might, it's unlikely they'll do something like that, but you never know. I wouldn't be surprised. So we now have two boundary conditions here, and we're going to use them to find P and Q. Which one should we use first? Well, it's this one. Why should we use it first? Well, because T is 0, which means Q is this term is going to disappear. So, when T equals 0, H equals 27, which means that 27 equals P to the 3 over 2. So P is 27 to the 2 over 3, which is 9. Okay. We know that when T is 10, H equals 8. So 8 equals 9, because we now know P, minus 10Q to the 3 over 2. So 9 minus 10Q is 8 to the 2 over 3, which is 4. So 10Q is 5, Q is a half. Now notice how we don't need to write down the particular solution of the differential equation, because the question just says find the values of P and Q. I would, because looking forward to the part D that I haven't written down yet, we're going to use the equation. So if you were asked to find the differential equation, you would then write down the final equation, which we've got here. But for this question, all you need to do is find P and Q, and we've done that. P is 9, Q is a half. So we've done a whole bunch of maths. The last thing we're going to do is use our final equation to solve or to find some values of time, which is typically what you'll do if you ever go and do modelling for a career or kind of mathematical modelling for a career. Is typically, right, let's do a bunch of stuff to find the equation so we can use it. This is the point of getting to here. Albeit this is very straightforward, because we're trying to find T when H equals 1. Okay, so when the height is 1, because remember, H is the depth of the water. So we want to find when H is 1, what is the time? So 1 equals 9 minus a half T to 3 over 2. Because of the way 1 works, undoing that is nice and easy. So we know that 9 minus a half T is 1. A half T is 8. So T is 16. The key thing here is the question doesn't say find T, it says find the time in minutes. So we need to relate it back to the situation we're in. So when the depth, actually let's reword that. The depth of water is 1 meter after 16 minutes. And we are done. I'm aware this is quite a long video, but that's the thing with differential equations, is these questions are quite long. They can be worth a decent chunk of marks, but if you take it slowly, like we've done here, and do it in steps, particularly if the question, like this example, guides you through those steps, don't panic. Typically, as you saw with parts A and B, they were both show that questions. So even if you couldn't do those bits, you can still do parts C and D. They're using your equation to work out stuff. And that's very typical of these questions. Very rare will they say in the exam, okay, here's a differential equation, solve it and use it, with no guidance. Because then if a student can't do that first part, you're just going to lose a ton of marks for no reason. So more likely, if it's particularly difficult like this one, they'll walk you through it, they'll take it through in steps. Key thing with this example is don't freak out. Don't panic about renaming your variables. Or, sorry, renaming your constants, not your variables. Never rename your variables. You're allowed to rename your constants. As long as you're clear what the new constants mean, you can do that even if you're not told to. Like with this one, we worked out that P was 9. If we go, and that Q was a half. If we go right back to where we started, we got that Q, what was Q equal to? Q was minus K times 2/3. So Q was minus 2 over 3 times C times the cube root of 100 pi over 100 pi. I don't know about you, but working out that Q is a half is much easier than working out what C is for this. Because regardless, you can do it, but it'll still be a mess. This is a much neater equation than leaving C in there. And that's kind of the point of this example. So hopefully that was useful. So you can now go away and practice the more in-depth differential equations questions in your textbooks or in your exam papers. Thank you for watching.